Last time, we talked about processes and how each process gets the illusion that it has its own private control flow. We also introduced the idea of virtual memory as a way to give each process the illusion that it has its own memory to hold its full 2 to the 64 byte address space. In this lecture, we're going to dive deeper into how virtual memory works to construct this illusion for processes and to share the limited physical memory among many processes. More generally, this lecture continues our service level tour about the interface between the application processes you write and the underlying operating system. Before we can really talk about virtual memory, though, we need to fill in some long-omitted details about the storage hierarchy that we've mentioned in passing a few times. And then we'll discuss locality and caching, which is fundamental to the perceived performance of a small, fast memory, but the capacity of a large, slow memory. Your processor is running at the sub-nanosecond level. If you've seen a processor advertised as something like 3 gigahertz, that means the processor cycles 3 billion times per second. Think of the cycle as a click to go to the next step, as it works through its lowest level operations. But this means that it needs storage to work at that same speed in order to keep up. If storage is slower than the instructions, then the instructions are always waiting for the source or destination to finish reading or writing, and they are artificially slowed down to take more cycles than they otherwise would. On the ARM processor, as we've seen in previous weeks, most instructions use register operands, which allow the instruction to run at full speed. But to accomplish this, the ARM processor has to put the registers on the processor chip itself. This makes them tremendously expensive and tremendously power hungry, and so, as a balancing act, they're very small and there's quite few of them. There are only tens of these, making up under 1,000 bytes total. This is typical of the storage hierarchy. Very small, very fast, very expensive, pyramiding out to very large, very slow, very cheap. But after the registers, before the main memory, most processors have several levels of cache. Often 1 L1 cache per CPU core, 1 L2 cache per pair of CPUs, 1 L3 cache shared by all CPUs. Again, still close to the processor, but not quite as instantaneous as the registers. Modern processors have been adding more and more caches, and so the pyramid pattern is expanding out wider, but the pattern itself is the same. L1 caches are smaller and faster than L2 caches, which are smaller and faster than L3 caches, etc. And then you get to main memory, the RAM we've been talking about. Beyond RAM is secondary storage, your disks locally on the system, and beyond that, remote storage, for instance, backup tape or the cloud. The cloud has near infinite storage, but of course you have to transfer it over the network at what to a processor wanting to do 3 billion things per second is a glacially slow speed. So when we think about the storage hierarchy, what do we care about? We care about capacity. How much can we store? We care about latency. How long does it take to start reading or writing to or from a storage device? We care about bandwidth. Once we're doing it, how fast can we read or write? The difference between latency and bandwidth is the reason that when you want to read something from disk, particularly spinning disks, or via a network connection, you might typically read a lot. Maybe even more than you think you're going to need, because there's high latency, so it takes forever to get started. But once the data is coming in, it comes in at a reasonable clip, so the cost to read additional data is relatively modest once you've paid that upfront cost to read the first byte. The last item is volatility. Will the data stick around? In a register, it could be gone within a matter of instructions, but we have control over that. Memory is more persistent still, but again, it doesn't survive power outages and other considerations. But files on the disk certainly should stick around through power outages, and in fact for a very long time. And then of course there's remote resources, which should be essentially permanent. So let's put some numbers on these factors to consider the various levels in the storage hierarchy. Registers have essentially zero latency. They're on the processor and pretty much immediately available to the ALU. And bandwidth barely even makes sense to talk about with such a small capacity, but again, very fast. Caches have some latency, particularly noticeable versus registers, but at the first level or two, still remarkably fast, though the drop-off is considerable as you add more and more levels to the cache. But at this point, their capacity so dwarfs that of registers that it's easy to see why we keep adding more and more cache levels. Main memory is another factor of somewhere between 2 to 10 slower latency versus caches. This brings us up to almost 100x slower than registers, and that explains a lot about 2D versus 2E back in Assignment 4, when we got such stark performance improvement just from saying don't use the memory, use the registers. On the other hand, memory can be measured in gigabytes or now even terabytes, so there's a lot there, even if it's relatively slow. Continuing farther down the pyramid, SSDs, modern hard drives, are 10,000 times slower than memory in terms of latency, and spinning disks are on the order of 100 times slower than that. So it is absolutely critical to manage that transition between main memory and the disk. Because the processor finds main memory to be slow, again, think 2D versus 2E, and yet there are so many orders of magnitude latency increases just to continue to rise from there. This is the key question when we talk about how to manage the storage hierarchy. Here's all that info in graph form for a few representative processors. These are now almost 10 years old. The blue one came out in 2012, the green one in 2013. And so the raw numbers have continued to decrease bit by bit, but the multiplicative factor of latency between storage levels is still pretty much accurate here. And again, if you like graphs, this one's quite stark. That entire previous slide is the little bottom corner left that you can barely even see. This is why caching is going to be such a big deal. But of course, if you want to add potentially another order of magnitude, you can always go hit up Amazon or Microsoft or Google for cloud storage. Here, the sky's the limit, pun totally intended, for capacity, but again, latency is a killer. So in this environment, where the processor needs very fast access, but as sizes increase dramatically, latency does too, smart caching that takes advantage of program locality characteristics can provide the performance required without adding to chip complexity or cost. So let's dig in on that idea of locality. What we just talked about, where there's a tiny set of blazingly fast registers, then a still tiny set of small caches, progressively bigger and slightly slower larger caches, quite slow main memory, and tremendously slow disk, means that a program is doomed to fail if it can't overwhelmingly stick with using those first fastest levels of the hierarchy the vast majority of the time. But that's okay. This actually works, because most programs have a property that they only work with a small amount of data at a time. And when they use something once, they typically reuse it presently and frequently. So a process can have the data it needs and keep it in this super fast memory, while the rest of its data, the one that it doesn't need imminently, is in a much slower main memory. This property is called locality. And in systems analysis, we'll typically talk about locality in two dimensions, temporal and spatial. Temporal locality, from the Latinate prefix tempor for time, means that you're accessing some data, and remember that in the von Neumann architecture, instructions are themselves data. So you're accessing some data now, you're likely going to access that same data again soon, perhaps within the next few instructions that you process. A natural example here is in loops. For example, the increment step in a loop happens over and over again. The instruction is repeated frequently, and for a short loop, relatively quickly in time, and the access to the loop control variable that is updated is repeated frequently and again quickly in time. This is a benefit because if I pay the cost of keeping around the data that I just used, it will likely come up over and over again without having to re-get it out of memory. Spatial locality is more about the consecutive locations in memory. The idea is that if you're accessing some data now, you're likely going to access a bunch of consecutive data around that item soon. This is naturally found in arrays, where we traverse through from one element of an array to the next to the next to the next as a common idiom. It's also naturally found in instructions, because in the absence of branching, the flow of control is going to proceed sequentially from one instruction to the next, and even with local branching, they'll still be close. It's common not to jump very far in the text section. This is a benefit because if I pay the cost to bring in an entire block of memory containing just one memory item I need, I'll end up using not just that one item, but also a whole bunch of other items that I grabbed with it. Here's a concrete example. It's just computing the sum of an array of elements. This has really fantastic locality, both temporal and spatial. Temporally, the loop runs over and over again, so I'm accessing the same instructions over and over, and I'm accessing the same variables, I, n, and sum, over and over. Spatially, every single time the processor processes the instructions representing the plus equal, they're followed by the instruction for I++ that comes immediately after it. Recall that in assembly language, for loops are typically actually done as while loops with the increment step before the branch back to the top. And that branch comes immediately after the I++, assuming the unoptimized loop structure. But even with the optimized loop structure, after the plus equal and the I++, we'd then always have a CMP and then a conditional branch. As far as the data, we walk through the array consecutively. Every time we access a given element of the array, we are sure we're going to access that next element of the array the very next time through the loop. So if we were to bring in a bunch of instructions at a time, or a bunch of array elements at a time, we're likely to get them one after another. We take advantage of natural locality in code by having a cache. This gives us the ability to use frequently referenced items that we're going to access over and over, even if they're not quite repeated enough to stay in the registers. In particular, this is beneficial for instructions. We don't typically think of loading the instructions themselves into our general purpose registers for reuse, but they are often repeated. Further, instructions from the text section won't change, so we don't have to worry about an out-of-date copy of data that has changed, or writing it back once it's changed but leaves the cache. This is just a very small example of caching in this particular low-level systems topic, but caching is pervasive. It's a big idea of computing. Caching websites for faster geographically distributed access, caching DNS entries for resolution of IP addresses to domain names, even something as simple as the kill ring in Emacs, so that you can paste back any of the last several things you've cut. And in all cases, the goal is primarily speed, with a side of flexibility. We can think of storage as structured in levels. By convention, level numbers increase going down, so faster, smaller devices have lower numbers than slower, larger devices. As we discussed earlier, there's typically a trade-off between speed and size. Things engineered to be very fast typically are quite small, or perhaps the hidden variable here might be cost. Things that are engineered to be very fast are very expensive, and thus affordable only at a limited capacity. Reading bottom up on this slide, every additional cache level up, so towards a lower number, we store a subset of the previous level. The mechanics of cache management are that when we need to access some data, we're going to check for it in the lowest level cache, here level K. If it's there, then that's great. We've just gotten data that we need from a fast cache, and we've avoided going out to a big, slow main memory to find it. This is called a cache hit, like the kids' game Battleship. In the case where it isn't in level K, this is a cache miss. And in the event of a cache miss, we're going to have to go check for it in level K+1. If we find it in level k plus 1, that's better than another miss, but it's still not as good as having hit in level k. Under the assumption that temporal locality is common, we're going to try and avoid future cache misses on this same data, and so we'll put it into level k. This, though, means that we're going to have to kick something out that's currently in level k. And depending on the exact details of semantics or policies, if the value in the cache has changed since it was first loaded into the cache, evicting it might mean we have to write it out all the way down the chain of caches, maybe even all the way to main memory or the disk. So we're paying for not having had a hit in level k by having to get the sought item into a lower level. And we're also potentially paying to do the eviction of the item it replaces. We definitely want to prioritize getting cache hits and minimizing cache misses. Ideally, to maximize hits and minimize misses, the subset we store at each successive level up is the subset we'll most need in the near future. But it's impossible to know the future, so that's why locality properties of our programs are important. We can't know absolutely what's going to be needed next, but we can design algorithms to exploit these patterns. Eventually, though, we still have to determine not just what to put in the subset in cache level k, but also, when we add something new, what to evict. If our premise is that we should always have the things we'll most need in the near future, the best possible eviction policy is to evict the block that we will next access the farthest in the future. Ideally, one that we'll never access again. And similarly, the worst possible policy is one that always evicts the data that we're just about to request. This would reduce our access time to be that of main memory for all operations. In general, neither of these is actually feasible because we don't have an angel oracle to tell us the perfect move to make, nor do we have a devil oracle to tell us the perfectly wrong move to make. When designing a policy that we can actually use, we have to trade off how much work it is to determine the right data to be evicted versus the benefit of choosing that correct data. This ends up meaning that at a very low level, like the instruction cache for a processor, the policies are typically pretty simple because they have to be implemented in hardware or at the very lowest level OS code. But up at higher levels, for example caching web pages, there can be extraordinarily complex policies because the storage to maintain metadata or the algorithmic time to compute the best evictee is insignificant compared with the gains of avoiding transcontinental data transfer. A reasonable eviction policy that doesn't rely on any oracle, and again comes down to the assumption that most programs exhibit good locality, is the LRU policy. Least recently used. That is, evict the cache member that has been accessed the least recently. If the past is a good indicator of the future, then if something hasn't been accessed for a long time, perhaps it won't be accessed again anytime soon. This is generally a good policy, but of course it has its limitations. Imagine a loop with 11 instructions and a cache that can store 10 instructions. When you hit that 11th instruction, in order to put it in the cache, you're going to kick out the first instruction, which will be the very next one up as we restart our loop. In this case, you end up never having a cache hit, even though your cache is big enough for over 90% of the data you need. This is, of course, a well-tailored counterexample that's probably unfair as a straw man, but this heuristic does have another less-than-great property. It's excessive to implement exactly. You must keep track of the time when each block was last accessed, and you have to keep an ordering among these. So a pure LRU is typically issued for an approximation thereof. Cache policy is a rich area of work, particularly in this approximation space, that continues to be a state-of-the-art research platform at many different levels of the system hierarchy. In the example I showed before, adding an array of numbers, it's a relatively simple example. Further, because it has great locality in both space and time, it's maybe too perfect a picture to leave you on the topic. Another classic example is matrix multiplication. Again, where smart, locality-aware code can have a tremendous benefit on performance. Note that this entire example is using the naive triply nested loop algorithm, not fancy things like Strassman's algorithm or Coppersmith-Winograd. But as an aside, Princeton Prof. Renraz did do some fantastic theoretical work on lower bounds for variants of this problem. So in this simple triply nested loop version, depending on which order we nest our loops, we can get significantly different performance. To get into this, as a quick note, perhaps a reminder, perhaps something new, C represents 2D arrays in memory in row major order. That is, we go across each successive row in a matrix, finishing off all of the elements in one row before seeing any elements in the next. But there's no reason it has to be this way. For example, Fortran uses column major order. But because of this row major order, it means that for good performance, when the expression A of I and j appears in a loop, I want the value of I to change more slowly than the value of j. This will result in accessing a bunch of sequential items in memory in short succession, and so it ends up being worthwhile to have read in the entire block of data from the cache, because you'll end up with a bunch of data read at once, and then you use all of it. That's spatial locality. Contrast that to the expression A of I of j, where it appears in a loop over a column. You're going to be jumping, in this case 18 to 21 to 24, non-consecutive memory. And thus, if the matrix were of a more real size for such a problem, you might have rows so big they take up the entirety of the memory block. So when you read in that block, you end up only getting to use one single useful value out of it, before you have to have a new access that's not in the block and thus is a cache miss. So let's come back to the matrix multiplication example. Recall that to multiply A times B, you take the row of A and the column of B, you multiply the pairs of elements by each other, and then sum up those products. And that sum becomes the single element in the result. You do this for all rows in A and all columns in B to create all elements of C. Here let's assume 3 square matrices of the same size. Here's a piece of code. It's arguably the most natural way to write this matrix multiplication. In the innermost loop, we're accessing B by column. K is changing more than J. But the other two have the preferred pattern. A and C we're accessing by row. So that's good performance. But since B is by column, that's bad performance. 2 out of 3 isn't bad, but we'll see if we can do better. Well, at least certainly things can go worse. Consider this alternative, which gets the same answer, but in a timing test, the code takes more than twice as long to run as the previous version. In the plus equals step, for C, I is changing faster than J. For A, I is changing faster than K, and for B, K is changing faster than J. In all cases, we're going through by column, as opposed to by row. So all 3 of these are going to exhibit bad cache performance. Here's a third version. In this version, we can see that we're going across the row in all 3 matrices. For C, J is changing faster than I. For A, K is changing faster than I. And for B, J is changing faster than K. And indeed, our timing test shows out maybe 10% faster than the first version. One might note that a smart compiler could maybe do this optimization for you, because you can see it's just a sum of products and thus it's commutative and associative. But that's sort of beside the point here. The takeaway is that locality and caching can have significant impact on what is an otherwise equivalent computation. And so certainly in the general case, we can't rely on the compiler to be able to make adjustments like this for us, but we may be able to look at it ourselves as programmers and see these patterns. To finish up, before moving on to virtual memory, here are some general observations about the hierarchy. We have trade-offs when considering how much data to fetch at a time. If we use a large block size, it takes up more time to transfer, but the data transfer happens less often. On the other hand, we're also more likely to have to evict things out of the cache because we're using up more space. But if we have more of it at one time, we're more likely to be able to exploit spatial locality. So this is a trade-off. Typically, lower down in the pyramid means that you have slower data transfer, and so we do larger block sizes. But this is just a heuristic. The second question we might have is who manages the cache? And again, the answer may change at several different levels. As we saw in Assignment 4, the use of registers is managed by the assembly language programmer, or the assembler or the compiler as the case may be. The next level, L1 through L3 caches, are managed by the hardware because they have to operate really quickly and make intelligent decisions about workloads and persistence versus eviction. So that's when the register needs to get something, it's more likely to get it quickly. Ideally, it's coming from here and not further down the pyramid. Main memory is managed by the operating system, along with the hardware. Because this level requires more advanced algorithms, but they're worth their complexity due to the exponential blow-up in latency, and because this is the level where we can start to make informed decisions about how to manage virtual memory access. And in secondary and remote storage, the end user typically is the one who decides what files are worth saving, backing up, etc. So in light of that last slide, if you're interested in the other levels, the L1 through L3 caches are typically covered in a course like architecture, in this case the sequence 375-475. The secondary storage and tertiary storage, that fits more into operating systems or distributed systems, respectively. But the remainder of this lecture will be more in-depth discussion of just how the OS and hardware team up to manage the main memory, and especially the transfer of main memory data into and out of the disk. Last time we discussed how the OS presents a process with an illusion that it has a gigantic array of 2 to the 64 addressable bytes of memory. Of course, in practice, processes aren't using all that much memory. But for that good news, there are two issues. There are many more processes than just the one, and the actual hardware doesn't have anywhere near that much memory anyway. So we're going to have to use the disk to manage memory that it can't fit in physical memory at any given time. To manage this incongruity, the virtual memory system uses main memory as a cache for the disk. And just like when we were talking about block size for caches, we can't think about memory in terms of that many separate addressable bytes, even though the program's thinking of it that way, because we surely can't. Surely the OS would grind to a halt if it was forced to pay the price to go to the disk to read a single byte. It's much cheaper to read a large chunk of data, because once you've bitten that latency bullet, reading additional contiguous data doesn't really take that much more time. And due to spatial locality, there's a good chance we were going to end up needing that subsequent consecutive data anyway. So we divide the memory into pages. And every transaction of reading virtual memory from disk into main memory, or writing it back out from main memory onto disk, is going to happen at a granularity of a page. On our system, that's 64 kilobytes. From here, seeing this reality, we can start to ask, how does it work? To do so, we'll need to distinguish between physical addresses and virtual ones. Because as I said last time, even at the assembly and machine language levels, as low as they are, the addresses you've been working from are an illusion. At this point, we can subdivide the virtual addresses that you've become familiar with into two components, a page number and then a byte offset within the page. So the upper bits indicate which page we're talking about, and the lower bits indicate the offset onto that page. The physical address is also going to be broken down like this, but rather than identifying a location in the virtual memory space, it addresses bytes in the actual physical hardware memory. The physical address is known only to the OS and hardware. The OS is responsible for translating back to virtual addresses for the application. In order that the operating system can do this translation seamlessly, there's a requirement that the page size be the same in the virtual memory and the physical memory, and that the page offset of the two addresses correspond. This means that the OS only needs to keep track of the mapping of full pages to full pages, not individual bytes to individual bytes. So the offsets have a relation, but the page numbers do not. There's not even an ordering requirement. Virtual page 1 might be at physical page 9, while virtual page 2 is at physical page 3. In fact, physical addresses may not even be the same size as the virtual address. After all, none of our machines has 16 exabytes, that's 2 to the 64, so they certainly don't need full 64-bit addresses. In practice, while the virtual address will have 64 bits, on ArmLab the physical address has less than that, only enough to address all of the actual physical memory. But they will have the same offset size, since the offset values have to be the same, and the offset size is determined by the page size. There must be enough bits to uniquely identify a page size worth of addresses. So in this case, on ArmLab, the page size is 64 kilobytes, so we need 16 bits to store those offsets, because 64 kilobytes is 2 to the 16. That leaves 48 bits to store the virtual page number, and thus there are 2 to the 48 virtual pages. But as noted, the physical address's length is driven by the size of the physical memory. Each ArmLab machine has 128 gigs of RAM, that's 2 to the 37 bytes of memory, so with a 64 kilobyte sized pages, that leaves 2 to the 21 physical pages required to cover all of the RAM. So now that we get to the crux of virtual memory, how do hardware and operating system work together to do it? And hopefully it's mostly hardware, because hardware is fast, and we know the operating system is just a program. It's a really fancy program, but just a program that manages all the processes. So anytime it's running, those other processes aren't, and we'd like to avoid that as much as possible. As it ends up, the hardware does, as we wanted, do most of the heavy lifting. The OS becomes involved only when it has to go to the disk. The key data structure for managing the physical memory, virtual memory translation is called the page table. It's maintained by the hardware. In the page table, every virtual page that you have will be mapped to a particular status. If it's in the physical memory, that status will be the physical page number it's on. If it's on disk, because it's been swapped out, the page table contains that disk address. Or perhaps it hasn't been created at all. Consider the program break, the huge space between the stack and the heap. It remains unmapped. It will likely never be used, so why bother creating entries for it? And even if it does end up getting used, it would only ever be used after a break system call. So the OS would have been alerted to go and update the page table anyway. Note that we're only mapping the page numbers, not the offsets, because again, the offsets are the same in either virtual or physical memory. So let's see a simple example. We have a single process in its virtual memory. And in its page table, we have the virtual page number and either the physical page it's located onto, a location on disk, or no information at all if it's unmapped. We can see that, for example, virtual page 0 is at physical page 2 in the top row of the page table. And on the far right, we indeed see that virtual page 2 is paged out to disk at location X. So before we dive into the example, let's make sure we can figure out what the page number and offset are, because we can't well use the page table indexed by virtual page number if we can't calculate that. Assume this is the ArmLab machine with 16 bits for the offset. If the offset is the lower 16 bits, that's 4 hex digits, so that's 0002. That means the page number is everything above that. A whole bunch of leading zeros, and then 4. So the answer is A. Now let's move on with the example. We want to access that address, hex 40002, which we know from the previous slide is virtual page 4. The hardware is going to note, using the page table, that virtual page 4 maps to physical page 1. And that's a page table hit. Great. At this point, we've only had the hardware involved. The OS hasn't had to do anything. So now the next question is, what is the corresponding physical address for this virtual page? The offset is the same size and remains the same, 2. The physical page comes straight out of the value in the key-value pairing of the page table, which was 1. So the physical address is hex 10002. That's answer C. So now we have a mapping to form the physical address. And again, the hardware can do it. It does just what you did on the last slide. So with that, we can go out and actually fetch the data from that physical address, hex 10002, and give it to the process executing. The next operation is memory location hex 20008, which we can calculate as virtual page 2 offset 8. The hardware will see the virtual address and attempt to look it up in the page table to find where virtual page 2 is in physical memory. But when it consults the page table, it finds not a physical page, but a disk location. That's a page table miss. The hardware generates an exception, a page fault. This is establishing an error state and relinquishing control to the operating system to come clean things up. So what does the OS do? First, it runs a page eviction algorithm to determine what to kick out of physical memory. Let's say it chooses virtual page 6 in this case. It will then talk with the disk drive to tell it to write back out virtual page 6 and write back in and read back in virtual page 2. It will update the page table to make this change, and then it will return control to the process to try that same instruction again. Basically telling it, you'll find virtual page 2 this time, I promise. Realistically though, this OS work takes approximately forever in the context of a running processor, so in practice right now there will almost certainly be a context switch away from our process while the OS does its thing. So, back in our process eventually, we again try to access virtual page 2, just as we did before. Last time we got a page miss, but the hardware does its mapping virtual page 2 to physical page 3, and now it's a page hit. With the successful lookup, the hardware forms the physical address, 30008, and it fetches or stores the data as appropriate. So for this operation, the hardware started, ran into problems, had to cooperate with the operating system, but then was able to finish it out as planned. Finally, let's try to access virtual address 10009. That's on virtual page 1, and we know what happens at this point. The hardware consults the page table. But when it does, it finds that, well, there's no mapping there. This is a page table miss. The hardware will again generate an error state and ask the OS to take over. But whereas before it generated a page fault saying, this page I know about, but it's paged out to disk. Now it generates a segmentation fault. This page is completely unmapped. The OS again takes over to handle it, but alas, the default handling of a seg fault is terminating the process. So that's the concept of virtual memory. It's how virtual memory is implemented using a virtual and physical addresses and page tables. I'd imagine, though, that this description could lead to some immediately obvious questions. So let's address some of them. Where do we store the page table? Well, it's in memory, naturally. But that just begets another question, which is, but what if that page of main memory is swapped out to disk? That would present a catch-22. If the page table is on disk, we have to load the page table from disk into memory. But in order to figure out where the page table is on disk, we have to consult the page table, but it's on disk. So under the premise of that classic medical answer to the complaint, it hurts when I do this, of, well, don't do that, the OS makes sure that the page table is never swapped out. Another question to consider is if it means that each time we dereference a pointer in assembly, that's actually doing two separate memory accesses. One to access the page table, in memory, and then one to do the actual lookup. Considering that accessing memory is hundreds of times slower than accessing registers, there's a good reason to be concerned. But I have good news on this front, and it's what we started out the lecture with. It's a cache. First of all, since page tables are accessed frequently, they're probably pretty much always in the cache. Even better, most modern architectures, including ARM, have a page table cache built into hardware, the Translation Lookaside Buffer, or TLB. This means that the slides we just showed with the trace aren't quite true, but I'm sure you're getting used to that. Just when you get the hang of it, we're telling you to look under yet another even tinier hood. So the TLB is a cache of page table entries. When the hardware has to look up a virtual address, it first consults the TLB on its own chip to see if there was a recent request for that virtual page. If so, that's a TLB hit. It's able to immediately return the physical page and can service the requested operation. If not, that's a TLB miss. Now we'll go on to the page table itself, which, as noted, will likely/hopefully be in the L1, L2, or L3 cache, and thus get a cache hit from a slightly higher level cache. Perhaps you recall from last lecture, I posed a question about the relative benefits or disadvantages of the virtual memory abstraction. In particular, its completely abstracted away use of swapping in and out between physical memory and disk, versus directly accessing physical memory. One thing we mentioned was how this improves security, because each process ends up with its own private memory, and it's not readable or writable by any other process. But the answer was B. It came with this red down arrow, because at the expense is performance. Each process's data in physical memory risks being evicted by another process's memory, or even other parts of its own virtual memory. In this lecture, though, we've started to see how we can ameliorate that red arrow in B by managing the virtual memory effectively and capitalizing on natural locality that exists in your program. The real answer here is there's not a huge effect in speed, and that's why virtual memory is pervasive. So let's come back to some high-level summary of the many ways that our concept of virtual memory affects the design and operation of modern computers. We saw last time the idea of context switching, which on its face should be formidably expensive. But we don't actually have to save all the virtual memory in a context switch, because it will be lazily evicted as the new process needs more space in physical memory. We just need to update the registers to your saved values and start using your page table, and the virtual memory will swap in the memory you need, swapping mine out as it goes. And we do get the improved security protection between processes because they only have access to their own pages in physical memory, not all pages in physical memory. And further, even their access to their own pages is indirect. But it also provides protection within processes, as the page table entries indicate various permissions, including read-only protections on RO data and text. Virtual memory also allows every process to have the same memory layout. For example, some sections always start at some static address. Additionally, it allows multiple processes to reference the same code in physical memory. For instance, we don't need every single process to pull the machine code for printf into physical memory. Since we can mark it as read-only, we can have only one copy that is the target of mappings of many different processes' page tables. And finally, the next two slides offer a preview of your next two assignments. In Assignment 6, you'll see that the way virtual memory works has significant implications on how dynamic memory is handled within a process, and the communication between a process and the operating system in implementing it. And for Assignment 7, you'll implement a program that has multiple processes. And once again, the beautiful abstraction provided by virtual memory makes some of the nitty-gritty process management tractable where it otherwise might not be. Next lecture, we'll continue talking about memory, specifically how dynamic memory management can be implemented as a lead-up to Assignment 6. In fact, all of the remaining lectures are directly targeted at the final two assignments, because the second lecture next week will begin covering material relevant to Assignment 7. We're truly entering the home stretch.